Hello everyone, in this video I will talk about how to solve AP Physics C, Electricity and Magnetism for 2023 free response question number 3. So it's a circuit problem that involves the capacitors and resistors. Let's look at this question first. The circuit shown consists of a battery of EMF here, resistors 1 and 2, they're connected in parallel, each with resistance R. Capacitors 1 and 2 with capacitance C and 2C. So this is C and capacitor 2 is 2C. And a switch. The switch is initially open and both capacitors are uncharged. At time t equals 0, the switch is closed to position A. So now it's closed to A. Question A. Write but do not solve a differential equation that can be used to determine the charge Q on the positive plate of capacitor 1 as a function of time t after the switch is closed to position A. Express your answer in terms of EMF, R, C, Q, and T, and also fundamental constants as appropriate. So we know that if we close the switch to A, it's a RC circuit. Now, one thing is important is that the resistors here, the R that we talk about in RC circuit, now consists of two resistors in parallel. So we should first calculate the total resistance of the two resistors, and then we can use that total resistance as the R in the RC circuit. But to write down the differential equation, we should use the Kirchhoff's rule. So let me first draw the circuit here so that I can draw a loop to write down the loop rule. Okay, so now we can replace this part of the circuit by R over 2. Okay, so that's the total resistance from a parallel connection of the two resistors. Now let's assume that the current direction is this way. Which is actually the actual current direction. So the positive terminal here will apply a current in this direction, okay, going through the capacitor C, and not going through actually charged capacitor C. So the upper plate here will carry positive charge, and lower plate will be negative charge. And we need to also apply select a travel direction. So I'm going to say it's clockwise. So if you're not sure about what the meaning of the travel direction, you can refer to our app, Physics Master, where we have the discussion of the rule. And it basically means that you want to visit every component of the circuit. And the travel direction is the way that you're going, it's the direction you're going. And the reason we choose this direction is because in a way that we're going along the circuit, the potential will either increase or decrease. And for example, for the EMF here, if I go this way, the potential increases, right? Because we go from the negative terminal to the positive terminal. So that's an increase of the potential as we move this way. And if you move the other way, let's say I pick a travel direction in a counterclockwise direction. Now you're going to move from the positive terminal to the negative terminal. So that means that the potential decreases. So that will give us a sign difference in writing down the potential as we cross this element, this circuit element. Okay, so now let's go back to writing down the loop equation. Now if I start from here, the first element I move across is the battery. And in this direction, the potential increases. So I'm going to write down a positive EMF. Okay, now the current direction is in the same direction as the travel direction. So we're going to say as we move across the two resistors here, the upper side has a higher potential than the lower side. So that means that there's a decrease of the potential. So we should add a negative sign here. And then using current, Ohm's law, current times the total resistance R over 2, we can get the amount of decreased potential. Okay, now we move to the capacitor. Now remember, the upper plate is positive charged and lower plate is negative charged. So if I go this way, from upper plate to lower plate, the potential decreases. Okay, so we need to subtract the potential difference of the C. And potential difference of C is calculated as Q over C, right? So that's the charge stored in the capacitor, and C is the capacitance. So now we go back to the starting position. So the potential difference should be 0. Okay, so now get 0 here. So that is the loop equation we can write down. Now let's change it to a differential equation. Now the differential equation is about the charge Q. Okay, so we know that's a relation between I and Q. I is dq dt. Okay, and according to the setup here, because we're charging the capacitor C, right? So the Q is increasing. So dq dt is positive. Right? As a function of time, Q is increasing, so dq dt is positive. That means that the current should be positive. So that's why it's important that you assume a current direction this way, because that is the correct current direction. So when we solve the differential equation here, I should get a positive value for this I. And if I pick another current direction, let's say that way, assume that current direction, then I should add a negative sign here. Okay, just something that you need to be careful about. You need to be consistent. In our case here, this I is positive, so we should have a dq dt positive here. Now let's combine these two equations and then replace I with dq dt. So we get, let me rewrite this term, dq dt minus q over c equals 0. So that is the differential equation required in part A. Now let's look at part B. On the axis shown, sketch graphs of the surface charge density sigma on the positive plate of capacitor 1 and the total power P dissipated by the resistors as functions of time t from time t equals 0 until steady state conditions are nearly reached. So the solution to this differential equation, so let me first rewrite that equation as the following. So if you remember like RC circuit, you can write that solution directly. So let me write this down, and then later I will explain how I get that. So Q is going to be Q max times 1 minus e to the negative t over tau. Okay, now Q max is the maximum charge that can be stored in this capacitor by such a circuit. And we know that the maximum potential difference C can obtain is the battery's EMF, so it's EMF. And according to the definition, right, we have capacitance C here, so let's multiply C here. So that will give us the maximum charge possible stored in the capacitor C here after an infinitely long time. Now the tau here, right, is called a time constant. It's given by the total resistance in the circuit. We call it R times the capacitance C. Now in our case here is R over 2. So tau is R over 2 times C. Okay, so that gives us the parameters here and also there. Okay, that's the solution. But now let me explain like how you get this one exactly. You should get that already from your textbook reading or from your lectures. But for our case here, I want to explain this one clearly how you get the solution here. So let me first reorganize all these terms, and then I will separate the variables in the differential equation here. Okay, so the two variables we have here is Q and T. So let me group EMF and Q over Q minus and also Q over C here together, and then on the right side I'm going to move R over 2 dq dt to the right side. Okay, now the left side only contains a charge Q, so I'm going to group it with the dq here and then move dt to the left side. So I'm going to move 2 over r dt to the left side, and then right side is dq over EMF minus q over c. Now let's do the integral here. The integration bounds goes from 0 time to a time t, and then I will change this t to dt prime so that it's a variable, and t now is a fixed final time. Q here, we do the same thing. I'm going to change this one to dq prime and also q prime here. And then the charge goes from 0 to a final charge q, right? Okay, so now let's integrate both sides. The left side will have, that's easy, so it's 2 over r and t minus 0, right? And the right side is, so this one is a log function if you integrate the equation here. But before we get to that log function, we need to pair up the same coefficient here. So you want to add a negative times c here, negative c here, so that you can have a negative q prime over c in the derivative. And then that will give us this log function. So that log EMF minus q prime over c, q prime goes from 0 to q. Now let's plug in the lower and upper bounds. When I plug in upper bounds, I get EMF minus q over c. When I plug in lower bounds, I get EMF. Minus q over c and then EMF. Okay, so let's move negative c to the left side. Okay, so let's put the exponential on both sides. E to the negative 2 over RC t equals the right side EMF minus q over c over EMF. Okay, now since I need a an expression for Q. So let's reorganize all these terms. Let's multiply EMF and then also move the Q over C to the left side and the whole thing here to the right side. So we have Q over C equals EMF minus EMF times E to the negative 2 over RC times T, and that gives us Q equals EMF is a common factor. Let's pull it out and then multiply C here, and then inside the square bracket I have 1 minus E to the negative T over tau, okay, where the tau is RC over 2. Okay, so that's basically how you get the solution here that I talked about earlier. But if you remember, like from the textbook, you can write this down directly to save time during the exam. Okay. So now the remaining question is how to plot that curve. So let me go to the next page. So the charge density is Q over S. So I'm going to assume S is the area of plate of the capacitor. So that equals EC over S, 1 minus E to the negative T over tau, where tau is RC over 2. Okay, so you're going to plot an exponentially increasing function. So we need some initial and final value here. So t equals 0, that's the initial value. We know sigma equals 0, and when t equals infinity, this term disappears. The exponential term disappears. So sigma equals EC over S. Okay, so that is the maximum value we can get for the charge density. So if I plot the charge density as a function of time, then I should get 0 here at the beginning. And let's draw this horizontal dashed line to represent the maximum value. Okay, so we're going to approach that in an exponential function. So the exponential function will approach that indefinitely. However, we can never reach it. Until t equals infinity, which we know is impossible, right? So you should draw a curve that look like that. And also in my solution in the app, I also write down the like in the tau. When t equals tau, this value here is 0.63, the maximum value. Okay, so that's kind of like a special point. When t equals tau, you get e to the negative 1, and then you can calculate that ratio here, 0.63. Okay, so now let's look at the power dissipation for the two resistors. The two resistors, they're connected in parallel, so we already know that the total capacitance is R over 2, right? So let me see. Oh yeah, the total power by the two resistors. So we should use the two resistors. So the total resistance is R over 2, and we also know the power formula is I squared times total R, right? So that's R total. So we should know I here in order to calculate R total. So now I is given by dq dt. Let's look at this derivative here. So Q again is this equation. So if I do dq dt, I will get the I will get rid of the first term, which is 1 is a constant, so it will disappear. And there will be a negative sign here. So negative EMF times C times the exponential function. But before that, I need to also write down the coefficient of t here. So that's negative 1 over tau. Before I write out this negative t over tau, right? Because the derivative of the t here will include this coefficient, negative 1 over tau. So tau, remember, is RC over 2, so it's 2 over RC. And we cancel out the negative sign, cancel out the C, so we get 2 EMF over R e to the negative t over tau. Okay, so let's plug in this I. So power equals 4 EMF squared over R squared e to the negative 2t over tau. Okay, so this square here give us the factor 2. And R total is R over 2, right? So that means that finally we get 2 EMF squared over R e to the negative 2t over tau. Okay, so that is the maximum value in the power dissipation, and that happens at the beginning. So when I check t equals 0, the power here is 2 EMF squared over R, and that is actually the maximum value. Now if I check t equals infinity, the power will be 0. Okay, so that's the minimum value. It's also the steady state when there's no current flowing in the circuit. Okay, so I'm running out of space, so let me get rid of something here so that I can draw the two diagrams together. Okay. All right. So that's power P times T. So at the beginning, the power is maximum. So I should draw a point here. That's P max, or 2 EMF squared over R. And then it will decay to 0, right? So let's draw exponentially decay function like that. Okay. Now I also want to identify the when t equals tau. So I'm gonna do this. So in principle, tau is this tau will be half that tau. Okay, so I'm gonna draw it here. So that is about half the value. So that's tau over 2 here. When that happens, when the time instant is tau over 2, I should get the power, the maximum power here divided by E, by the natural number. E here, which is 0.37, the maximum value, times the maximum value. Okay, so let's look at question C. A long time after the switch is closed to position A, the charge on the positive plate of capacitor 1 is Q0, and capacitor 2 is uncharged. At time t1, the switch is closed to position B. Immediately after time t1, is the direction of the current in the switch directed toward the left, the right, or is there no current? So we're looking at the instant when the capacitor 1 is fully charged. So after a long time, C, C1 is fully charged. Then we close the switch to B. Then the capacitor 1 will charge capacitor 2 from that instant. So the current will flow this way. Okay. So you want to say for C here. So the current is to the right. Which you are charging C2, capacitor 2. Second sub-question, determine an expression for the total charge on the positive plate of C2 a long time after T1. So this one is at T1 instant. So now after a long time, C2 will be fully charged. So C2 is fully charged. So now think about this problem here. So we know that at the beginning the charge is Q naught on C1. So at T1, Q1 is Q naught, Q2 equals 0. So that's the like initial value, Q1i, Q2i. Okay. Now at the final value, we should redistribute this Q naught here into the two capacitors. Okay, so at t equals infinity, let's say we have Q1 and Q2. So their summation should be Q naught. So remember we said that we redistribute the total charge Q naught into C1 and C2. So that's why Q1 plus Q2 equals Q naught. This first equation we can write down. However, we have two variables here, so we definitely need another equation, a second equation, and that comes from the potential difference. So let's look back at the diagram, the circuit diagram. So these two capacitors, they're connected in parallel, right? Remember, the positive plate will charge the positive plate. So the two upper plates here, they're connected in parallel, which is why they both carry positive charge. Okay, so electron will move from capacitor 2's positive plate to the upper plate of the capacitor 1. So that's why capacitor 2's upper plate will carry positive charge. Okay, so the potential difference between the two capacitors will be the same, meaning Q1 over C1 equals Q2 over C2. Okay, and then we do know that C1 is C and C2 is 2C, right? So that means that Q1 is Q2 over 2. Q1 is half Q2. So if I plug this in, the first equation, I would have Q2 over 2 plus Q2 equals Q naught. And that give us 3 halves. Q2 equals Q naught. So Q2 equals 2/3 of Q naught. And then clearly, right, Q1 is 1/3 of Q naught according to the charge conservation. So let's question the second part of the question C. Okay, so now let's think about the third question. Derive an expression for the total energy ER dissipated by resistors 1 and 2 from immediately after time T1 until new steady state conditions have been reached. Express your answer in terms of C, Q naught, and fundamental constant as appropriate. So we know that the energy stored in the two capacitors, we know we can calculate these energies at time t1 and also at time t equals infinity, right, at these two instants. Then the difference between them would be the energy loss due to the resistors. So let's do that. So at t1, the energy of the two capacitors come from just the capacitor 1. So that's the initial energy. We would have 1/2 Q naught squared over C. Okay. Now at infinity, the final energy here for the two capacitors is still 1/2. Okay. And then for capacitor 1, I now have 1/3 of Q. So let's plug in 1/3 of Q naught squared divided by C. Okay. And then plus 1/2. Now it's 2/3 of Q naught squared divided by now for capacitor 2 is 2C. Let's simplify this expression here. So we do have 1/9 and then multiply 1/2, so that's 1/18. For the second term, I have this one is 4/9, and then there's another 4 here, so that's 1/9. And then the common factor Q naught squared over C. Okay, so if I sum them up, I will get E final equals, so that's 2/18, 3/18, so that's 1/6. Okay, so we do see a difference in the two energies. So the energy loss is the energy consumed by the resistor. So equals so we have 1/3 Q naught squared over C. So that's the energy dissipated by the two resistors. With the switch still closed to position B, the parallel plates of capacitor 2 are moved so that the separation distance increases by a factor of 2. Determine the ratio U2 over U1 of the energy U2 stored in capacitor 2 to the energy U1 stored in capacitor 1 a long time after the plates of capacitor 2 have been moved. Briefly justify your answer. Question D. Okay. So now we need to do the calculation again, just like when we did this part of the question. So that's a charge conservation. So we still have Q1 plus Q2 equals Q naught. Okay. Now one thing different is the capacitance of capacitor 2. So let me do this on this side. So in general, the capacitance is epsilon naught, the vacuum permittivity, times A, the area of the plates, divided by D. Okay, so here's the geometry. So we have a, let's say it's vacuum inside. So we have epsilon naught, and A is the area. So this area is A. And D is the separation between them, right? The distance between the two plates. Okay, so now we see we double the, so we double the separation, right? So D becomes 2D, okay? So that means that C2 becomes half the original C2, which is 2C, right? So we get C here. So that means that C2 now is the same as C1, meaning we should write down Q1 over C equals Q2 over C. Okay, so the potential difference across the two capacitors should be the same. That is the same as before, but now the capacitance of 2 becomes C, the same as C1. So from here, we don't actually need to do calculation. They're symmetric, right? So Q1 equals Q2 equals Q0 over 2. Okay, so now we need to repeat the calculation of the energy. So the energy U1 would be 1/2 Q0 over 2 square over C, which will be equal to U2. So that's why they are equal. Now question E, with the capacitor still charged as in part D, the switch is now closed to position A. Express your answers to part E. Question 1 and part E, question 2, in terms of RC, Q0, and fundamental constants. Question 1, derive an expression for the current I0 from the battery immediately after the switch is closed to position A. Okay, so let's look at the circuit diagram again. So once we turn the switch back to A, we actually separate the capacitor 2 from the circuit. So there's no, it's like there's no C2 anymore, and we're looking back at the charging circuit for charging RC circuit again. Okay, and remember now, capacitor 1 carries charge Q0 over 2. So that's like the capacitor is half charged. So we should definitely use that condition. Okay, so let's see. So Q now is Q0 over 2 equals, remember we have Q0 1 minus e to the negative t over tau, that expression we wrote down earlier. Excuse me. From this equation, we know 1 minus this exponential equals 1/2. So exponential of this negative t over tau is 1/2. Okay, so that's something that we can use later. Now let's look back at this E here. So I want to derive an expression for the current I0 at instant when the switch is closed back to A. So that's the current at this instant. So the exponential function here actually contains this instant. The time instant is actually contained here. Okay, so remember I equals dq dt equals EMF 2 EMF over R e to the negative t over tau. I remember that equation that we derived previously. So now we do have this condition. Okay, so this instant, let's call it T2 instant. Okay, so that's the T2 instant current. So let's plug in this 1/2. We get EMF over R. Okay, so that's the current I0. Second question, determine the current I infinity from the battery a long time after the switch is closed to position A. So now the position A, remember we still go back to the charging circuit, right? RC charging circuit. And then at t equals infinity, we should decay, right? The current here should decay to to 0, right? You plug in t equals infinity here, yeah, t infinity here, and then you get 0 here. Okay, so that's the answer. Okay, so that's all for this question. Thank you for watching.